In this example, we're going to find the general solution to a non-homogeneous linear system. And we will do so using all three methods to illustrate how they all connect, give you the exact same solution at the end. You have the system here, x prime equals 5, 3 minus 1, 1, x plus e to the minus 3t and 2. So let's first solve the homogeneous problem by looking for the eigenvalues and eigenvectors of this matrix. So the eigenvalues will be found by determinant of 5 minus lambda, 3 minus 1, 1 minus lambda, which is 5 minus lambda, 1 minus lambda, plus 3, is lambda squared, minus 6 lambda plus 5 plus 3, lambda squared minus 6 lambda plus 8, which factors as lambda minus 2, lambda minus 4. So for lambda equals 2, matrix becomes 3, 3, minus 1, minus 1. So an eigenvector is 1 minus 1. For lambda equals 4, it becomes 1, 3, minus 1, minus 3. So an eigenvector here is 3 and minus 1. So therefore, we can write the general solution of the homogeneous equation as C1, 1 minus 1 e to the 2t, plus C2, 3 minus 1 e to the 4t. I want to use all three methods to now solve the non-homogeneous equation. First, we have diagonalization. So based on our eigenvalues and eigenvectors, we know that we can take the matrix D, which is 2, 0, 0, 4, and P, which is 1, minus 1, 3, minus 1, and use this to solve our problem by diagonalization. First, we still need P inverse, and P inverse is going to be the determinant. So 1 times minus 1 plus 3, swap the diagonals, put negative signs on the off diagonals. This determinant here is 2, so this is a 1/2 in front. So this P inverse is going to be negative 1/2, negative 3/2, 1/2, and 1/2. Now for diagonalization, we know that we're going to solve for a new variable y, which is related to our original variable x, by x is p times y, and that y will solve y prime is dy plus p inverse f, where in our case this vector f is e to the minus 3t and 2. So what is p inverse f? P inverse f is the product, which comes out to be negative 1/2 e to the minus 3t minus 3, 1/2 e to the minus 3t plus 1. Which means, since our matrix D was 2, 0, 0, 4, this means that this system here is decoupled and can be rewritten as y1 prime, y2 prime equals 2y1, 4y2 minus 1/2 e to the minus 3t minus 3 plus 1/2 e to the minus 3t plus 1. I can now solve these two equations separately. The first gives me that y1 prime minus 2y1 is negative 1/2 e to the minus 3t minus 3. Integrating factor is e to the minus 2t. This becomes an e to the minus 2t y1 prime is a negative 1/2 e to the minus 5t minus 3 e to the minus 2t. Integrate both sides. Then multiply through by e to the 2t to solve for y1. You can do the same for y2, which satisfies y2 prime minus 4y2 is 1/2 e to the minus 3t plus 1. Integrating factor here is e to the minus 4t. So e to the minus 4t y2 prime, 1/2 e to the minus 7t plus e to the minus 4t. We integrate and then solve for y2, which then means our solution y is given by stacking these two up. And then finally we convert back to x by multiplying this by p. So x is p times y, which is the matrix 1 minus 1, 3 minus 1 times this vector, which we can work out. So in the first spot, we will get 1 of the first element plus 3 of the second. So I will get a 1/10 minus 3 over 14 e to the minus 3t. I will get 3/2 minus 3/4 And then we get a c1 e to the 2t and a 3c2 e to the 4t. For the second, I get minus the first and then minus the second. So I get a negative 1/10 plus a 1 over 14 e to the minus 3t. A minus 3/2 plus 1/4 minus c1 e to the 2t minus c2 e to the 4t. We can simplify out these expressions here. For the coefficient, 1/10 is 7/70ths. 3 over 14 is multiplied by 5 is 15, so 7/70 is negative 8. Negative 8 over 70 e to the minus 3t. 3/2 minus 3/4 is 3/4. Again, that's negative 7/70ths plus 5 is 2/70ths. Negative sign. Negative 3/2 plus 1/4 is negative 5/4. And so my answer then is negative 4 out of 35, negative 1 out of 35, e to the minus 3t, plus a 3/4 and a minus 5/4, plus a c1 times a 1 minus 1 e to the 2t, plus a c2 times a 3 minus 1 e to the 4t, which makes sense as this was part of our homogeneous solution from before. And this is the part here that then solves the non-homogeneous equation. That was diagonalization. Now, for undetermined coefficients, because our non-homogeneous part was an e to the minus 3t and a 2, our guess should be a e to the minus 3t plus b, which we can see is probably going to be right based on the fact that we got an answer of this form for the previous version of solving this problem. Now let's see what happens. If I differentiate this, I get negative 3a e to the minus 3t. Good. Now I'm going to plug this into the equation. And since the matrix here was 5, 3, minus 1, 1, we see that for this, I'm going to plug in a e to the minus 3t plus b. Then I want to add e to the minus 3t and 2. I'm going to rewrite these as column vectors now. Do the multiplication. What I'm going to see here is the vector 5a1 plus 3a2 minus a1 plus a2 e to the minus 3t plus the same pattern in terms of b's, and then plus an e to the minus 3t and 2. And I want to add these in to these two vectors where they belong to give a set of equations that looks like 5a1 plus 3a2 plus 1, negative a1 plus a2 e to the minus 3t, plus 5b1 plus 3b2, negative b1 plus b2 plus 2. And I want this to match the derivative from before. The derivative of minus 3a, it's going to be minus 3a1 minus 3a2 times e to the minus 3t. This gives me a system of equations to solve for a1, a2, b1, and b2. It is pairing up the e to the minus 3t terms. Negative 3a1 equals 5a1 plus 3a2 plus 1. Negative 3a2 equals negative a1 plus a2. And pairing up the constant terms, 0, because there's no constant term on the left-hand side, is 5b1 plus 3b2. And 0 equals negative b1 plus b2 plus 2. Let's work on the a's first. So for the a's, I can rewrite the second equation as a1 equals 4a2 and plug that into the first to give me that negative 12a2 equals 20a2 plus 3a2 plus 1. If I swing everything to the left, I will see a minus 35a2 equals 1, so that a2 equals minus 1 over 35. And then this tells me that a1 is negative 4 over 35. For the b equations, I can rewrite them as 0 is 5b1 plus 3b2, and negative 2 equals negative b1 plus b2. I'll take the second equation by 5 and add them together. I will get that negative 10 equals 0 b1s plus 8 b2s, which tells me then that b2 is negative 10 over 8, which is negative 5 over 4. Plugging that into the second equation here tells me that negative 2 minus b2 equals negative b1, where b1 is 2 plus b2, which is 2 minus 5/4 or 3/4. So that then tells you that my solution here should be the a vector, which was negative 4 over 35, negative 1 over 35, times an e to the minus 3t, plus the b vector, which is 3/4, negative 5/4, plus the general solution to the homogeneous equation. And that's how we would get that by undetermined coefficients. The other thing that we can use is variation of parameters. And the idea here is that my solution, x, is going to be capital X times u, where x is a fundamental matrix of solutions, and u satisfies that u is the integral of x inverse times f. So what is x here? Well, I have my general solution, which was c1 1 minus 1 e to the 2t plus c2 3 minus 1 e to the 4t. I can basically squish this together into a matrix to say that the matrix I want x here is going to be e to the 2t, negative e to the 2t, 3e to the 4t, negative e to the 4t. Basically just putting this as the first column and this here as the second column. Now, I need to invert this matrix. And it follows the same properties as normal 2x2 matrices. So the inverse here will be 1 over the determinant, which is going to be e to the 2t, negative e to the 4t, plus e to the 2t, 3e to the 4t, times, swap the diagonals, negative signs on the off diagonals. This bottom part here is a 2e to the 6t, because you get a minus here and a plus 3 here. So I will see a 1/2 e to the minus 6t times this matrix, and I can put everything there inside. If you look at this, the coefficients here are going to be similar to what we had for the inverse of p in the diagonalization case, and we'll actually see when we're doing these calculations, these look a lot like what we had for diagonalization in our first attempt at this. So that's x inverse. Now we need x inverse times f, where f was my e to the minus 3t and 2 that I had before. So x inverse f is that inverse matrix times our vector f, which was e to the minus 3t and 2. We can just work out this calculation. I'm going to see a 1/2 e to the minus 5t minus a 3 e to the minus 2t. And then I will see an e to the minus 7t plus 2 e to the minus 4t. Make sure to put the 1/2s on every entry when going through this matrix. I had forgotten that before, but they're in there now. And if you look back, we actually had this for our right-hand side when we were doing the first order equations from diagonalization. Now to get u, we have to integrate this. So integrating this vector here just involves integrating each part on its own. So we get the vector 1/10 e to the minus 5t plus 3/2 e to the minus 2t plus a c1. And at the bottom, I get a negative 1 over 14 e to the minus 7t minus a 1/4 e to the minus 4t plus a c2. Again, matching what we had for the diagonalization version. And then to find our actual solution, multiply this by x. Our matrix, fundamental matrix of solutions, which was, and then we can just write out term by term what this is. So we'll see a 1/10 e to the minus 3t when I multiply this by this term, and then plus a 3/2 plus c1 e to the 2t, and then plus the next term, which is going to be a negative 3 over 14 e to the 3t minus 3/4 plus a 3c2 e to the 4t. And at the bottom, I will get a negative 1/10 e to the minus 3t minus 3/2 and a minus c1 e to the 2t plus a 1 over 14 e to the minus 3t plus a 1/4 minus a c2 e to the 4t. And you can see where this is going. If I recombine terms again, I will see something exactly like I had before. I will get the 1/10 minus 3 over 14, negative 1/10 plus 1 over 14, e to the minus 3t. I will get the 3/2 minus 3/4, negative 3/2 plus 1/4. I will get the c1, 1 minus 1 e to the 2t, the c2, 3 minus 1 e to the 4t, and you'll see you get the exact same coefficients here from before, this being the negative 4 over 35, the negative 1 over 35, the 3/4, and the negative 5/4. So we have variation of parameters giving us this solution, undetermined coefficients giving this solution, and diagonalization giving the exact same solution. So all three methods give the exact same solution with a variety of approaches to how you want to go about solving them. Any of them are valid. They all work equally well. It's just which one you want to use to solve the problem that you're given, handling these non-homogeneous systems of linear differential equations.